Okay, let's start. So today we're going to finish the subject of path integrals, and the second lecture will be given by Sar. You will do the tutorial part, and then next week I'm going to devote, this will be the last week of the semester, so I will devote it to the Dirac equation. And I already tell you that this subject will not be in the exam because you didn't have a chance to exercise, but it will be, it's important for me to deliver it and that you'll know at least something about it. Okay? So, okay, so let's go back to the path integral. What we've seen in the last few lectures is a new formulation of many-body problems of identical particles, and that's the coherent state path integral. And we saw that one can do it for both bosons, identical bosons or fermions. In the case of the bosons, you are replacing, so let me write down just for reminder, a general expression for the partition function, the thermodynamic partition function, can be written as a path integral over the fields that we denote by psi. And you have to, what comes into the integral is functional of the field, which is the action. And for bosons, these psi's are complex fields. And for fermions, they are Grassmann variables. But in any case, there are some simple cases where one can solve it, and actually the only simple case that generally can be exactly solved is the case where you have free particles, namely the action is a quadratic expression in terms of the fields, and therefore the calculation really boils down to just Gaussian, solving Gaussian integrals for which we have an exact formula. So today I'm going to show you a trick, one possible nice trick how to approach interactions. So there are various tricks, but I'm going to mention two and do one, okay? Because we only have 1 hour and a half for that. So let me just remind you what are the definitions of these psi's. So when I'm writing psi, it's actually a field that most generally it depends on two indices. So we wrote it, or this is at least the most convenient basis, is to write it as an array of fields that have two indices. Here, alpha is a single particle quantum number, and n is the index of a Matsubara frequency. So n is an integer, and there's a Matsubara frequency given by 2 pi, sorry, let me write the most general thing. So pi t times 2n plus 1 minus zeta over 2, okay, where zeta is plus minus for bosons, fermions. This will be a notation we use all along. So therefore, for bosons, you just have an even multiple of 2 pi, of pi times T. Well, T here is the temperature. And for fermions, you have odd multiple, and that takes care of the anti-commutativity of the variables. I also want to put here another convention that we use units where h bar is 1, okay? And we define beta to be the inverse of temperature, so actually this is also Boltzmann, okay? Okay, I'm leaving it here up there. This will be throughout. Okay, so these are the fields, and generally S is some complicated functional, but in the case of free particles, so this is the case where the interaction part is 0, then S takes the form, and we call it S naught, this will be the convention, will be a quadratic expression, which you can write as, quite generally, psi bar G naught minus 1 psi. So G naught is a matrix, and psi is this vector, psi dagger is the row vector with psi bars, etc. Okay, so that's okay, and G naught is a matrix, and what appears in the action is denoted by is G naught minus 1, so the inverse of the Green's function. G is the Green's function. So let me just remind you what it is. Write it here like this. Put the index here. So the element, the matrix element of the Green's function is just defined. This is a definition. It's something like that, calculated, expectation value calculated in S naught. And the reason that we write it like this is that the matrix, so if you have an action S naught that has the coefficient of the quadratic expression is like this, when you calculate the Green's function, you get the inverse, okay? So therefore, I can define the action like this, and if I'm writing it more explicitly, it's a sum over n and alpha of psi n alpha bar, G, so actually, if I'm choosing the basis to be, the basis alpha to be such that it diagonalizes the single particle problem, okay, so it's the natural basis, and n is, as I said, is the Matsubara index, okay? So actually, the action has a simple form, right? So if the problem is diagonal in alpha, then this becomes, it's a delta of n prime, delta alpha prime times G naught, let me call it n alpha, where G naught n alpha is 1 over minus I omega n plus epsilon alpha minus mu. Mu is the chemical potential. Epsilon alpha is the spectral, the single particle energies. Okay? So, so let me write it like this. So it's G minus 1 n alpha psi n alpha, or to be more explicit, it's the sum over n and alpha psi n alpha bar minus I omega n plus epsilon alpha minus mu. It's just the inverse of this thing, right? The inverse of a diagonal matrix element, psi and alpha. Okay? This is quite general, and this form doesn't care whether these are the fermions or bosons. And there's just one, no, that's fine. In this definition, there are no prefactors and anything. Now, if this is all you have, just free particles, we can actually solve the partition function, and we get that Z naught is, it can be written as the Gaussian integral. I'm just copying it here. In short, and the result is a determinant of, and now it depends whether it's bosons or fermions, so it's the determinant of G don't get confused. So it's it's G to the minus, no, so it's actually G to the power zeta, right? So if there are bosons, it's the determinant of the inverse of this matrix, which is G naught. If there are fermions, it is G naught minus 1. Okay? So that's because of the funny algebra of the Grasson, that the Gaussian integral gives you the number appears in the numerator and not the denominator. That's where it's coming from mathematically. But anyway, this is the formula. Okay? And here when I write it as it's determinant of a matrix, which in the diagonal basis looks like this. Okay, that's G naught, and that's G minus 1 is just the energy plus the frequency. Okay? Okay, so this was quite general, and now let us take a specific example, and then we want to add interactions and see how we can deal with them, although it cannot be solved exactly. Okay, so so let me just maybe leave this formula here. This one we will need. And I want to discuss an example. electron-electron interactions in metals. Okay, so this is like the most fundamental problem in condensed matter physics. We think of metals as the simplest state of matter for electronic states because these are states where you essentially have free electrons. Okay, in a crystal there's a band structure, blah blah blah, but to a good approximation you can model it as free electrons. They also have spin half, and they just have kinetic energy, okay? But we know that they are charged particles and that therefore they are interacting. So there is an interaction. The interaction is not necessarily small, and that's a big problem. That's a fundamental problem, and the interaction is Coulomb. So we want to be able to deal with it. We already studied it in a few lectures ago in a mean field theory, and it gave us something nice, but we were worried that maybe if we go to the next order in perturbation theory, it will break down, right? Because there is no small parameter per se. The Coulomb interaction scale and the kinetic energy are comparable. Okay, so now I'll try to show you why it nevertheless works. Nevertheless, what we got from Hartley-Fock was fine. Okay, so first let us see what is the non-interacting part. Non-interacting part, as I said, is free electrons with kinetic energy and spin. So the quantum number that we usually called alpha now corresponds to two quantum numbers. One is the k vector and the spin, okay? And therefore that will be the basis in which we will write the free part of the action. So let me just write S is S naught plus S interaction, and S naught can be written in this basis. So let's see what are the energies. The energies epsilon alpha, if you don't have magnetic field, they don't depend on the spin, they just depend on the wave vector, and it is kinetic energy. Okay, so it's k squared over 2m, because I chose h bar to be 1. Actually, okay, let me be a little more careful. So it's actually this, okay? But h bar k is a momentum. Okay, so the momentum is a good quantum number. Now, because we are working in h bar equal 1, k and p. So k and p are going to be the same for us for h bar is the 1. Okay, let's do that. Okay, and now let me also define a function that I call psi, or let me call it psi of p. It's simply epsilon of p minus mu. Okay, we already used this definition in the when we studied the BCS theory. So it's just the kinetic energy relative to the chemical potential.
It's a different form of the energy? It's a different form of the energy?
No, it's not a different form. It's, let me here define, this is a definition. It's this energy. So P and K are the same, okay? I'm just changing the name. This is just the kinetic energy. And psi is this minus mu. Okay, where mu for fermions, I remind you that mu is the Fermi energy for fermions, right? So, right, mu is just the EF. So this is just measuring the energy from the Fermi energy. And therefore, it can be positive or negative, whether you have electrons or holes. Okay? But it accounts for that. It's convenient. Why do it's convenient to write it in this way? Because you can easily recognize that G naught, okay, the Green's function, let me write it as P. Sorry, before I do that, there's one more definition that I want to use. So here actually I have two indices. I have alpha, which in our case is K and sigma, but there is also the Matsubara energy. And in our case, because the quantum numbers are momentum, and the Matsubaras are, you can think of them as a set of energies, right? You can define a generalized momentum. Let me define it like this. Here I'm really following the notations of the book of Altland and Simons. So I define, when I write P without the vector sign, it's actually a 4 vector, which has the 0th component is the Matsubara frequency, and then there are the space components are P vector, the momentum, okay? And if you are in a 3-dimensional space, then P is 3-dimensional, and this altogether is a 4 vector, okay? So this is just a shortcut notation, because then we don't have to write sum over both n and alpha. I have just sum over P, okay, this P, all right? And therefore I can write, so actually let me write down S naught. I can write it as a sum over P of psi P bar. Now I have minus I omega n plus psi of P vector, psi, sorry, I forgot something important. There's also a spin index, okay, so the electron fields have actually two indices. One index, the P, includes the Matsubara sum and the Matsubara frequencies and the momentum, and the other is the spin. And the spin in this problem doesn't play a role because the energy does not depend on it. It just gives you the general C of factors of 2. Okay, that's all. Okay, so this is S naught. So you see it's very simple, diagonal matrix. We can easily solve the Gaussian integral. It gives us a determinant of this thing, essentially, right? That's all. Good. Now, what I want to do is to introduce the interaction. Okay, so let me first write it. S int, it's the part of the action that comes from the interaction, and I remind you where it comes from. Originally we wrote it as operator with a dagger. We turned them into fields. And I'm already writing the final result. We look like this. Here omega is, I'm going to write it definition here. Omega is the volume of the system, right? Because the momentum is a continuous variable if you have an infinite space, but in principle it's more, to be careful mathematically, we can define a finite but large system with volume omega, and then the p vectors will be quantized accordingly, and we can write a sum over p. So so there's a prefactor that contains a volume in space and a length in time, in imaginary time, and then there is a sum over 3 momenta and 2 spin indices, and it has the following form: P plus Q sigma, P psi bar of P prime minus Q sigma prime, VQ psi P prime sigma prime psi P sigma. Okay?
Now P is not 4 vector, right?
P is a 4 vector. All these P and Q, all of them are 4 vectors, and that's why, you know, I introduced this shortcut notation, because both the Matsubara frequency and the space momenta will have the same structure. Okay, so if you start from an interaction, let me just remind you where this comes from. We start from an interaction that is written in real space. Okay, there is some interaction between R and R prime, and between density at R and density at R prime. I'll just remind you of where it's coming from. And when you convert it to momentum space, noting that the interaction only depends on the difference between the coordinates, not on each coordinate separately, there's a conservation of momentum, but there is also, for exactly the same reason, there's also conservation conservation of momentum and conservation of energy in the scattering process. Okay? And that's why the Matsubara frequencies of the different fields also obey this structure that can be described as a diagram. I just remind you that you can think of this scattering process as electron comes with some P, and there is a P prime. Okay, and there's also the sigma, but the sigma stays the same. So let me just, for careful purpose, put the sigma. Then it emits a virtual photon or some gauge particle that carries momentum Q, and then this comes out with P minus Q. Plus, to be consistent with the expression, and this is P prime minus Q sigma prime. Okay? And there's a conservation of momentum, but again, it's a conservation of the 4-vector momentum. Okay? So this is why this notation is very useful. It really shortens everything, is just one type of index. Okay? So you can think of the time direction as another coordinate. Okay? Okay, so this is the interaction, and it is complicated because it's a function of 4 fields and not 2. So it's the solution for the partition function is not a Gaussian integral. Okay? But let me now write this more compactly, because we saw that a combination of 2 fermion fields can together give you a density. Where is this coming from originally? It's coming from an expression that in real space is an integral over densities, right? This is where it's coming from. It's r minus r prime, rho of r prime, right? It's a density, and this expression just comes from writing the density operator in terms of the electron fields, right? But we can express it in terms of the density if we note first of all that the Fourier transform rho q is a sum over p, and again this q is a 4 vector. Okay, it has also a Matsubara index and a q vector. So you can write it as a summation over p and sigma of p minus q, psi bar of p minus q, sigma psi p sigma. Okay? This is just a Fourier transform of the real space. So in the real space, the density is a local object. Okay, it's in the operator language it is psi dagger psi, but these are again the fields, and you sum over sigma. Okay, this is how it looks in real space. If you Fourier transform it, you get a convolution, and that's what it is. Okay. So using this definition, it's not really a definition. It's just what it is. We can write the interaction in a little more compact form as a sum over q of rho q vq rho minus q. Okay, let me see. Actually it doesn't matter which way it appears, because q is in the sum over q. You can exchange q and minus q because it sums over all positive and negative values equally. Okay, so you see it has a very compact form in terms of the density field. Okay, and in fact, if this is all we had, if S interaction was the only term in the action, it would suggest that we don't need to work with electrons. Just consider the density field as the degree of freedom, right? So it's like the density is a collective degree of freedom, but in our case, we have in fact 2 terms in the action that are equally important in a sense, assuming that indeed the physical parameters are such that none of them is negligible. Okay, one is coming from the kinetic energy, and it's quadratic in the electron fields themselves. The other is not quadratic in the electron fields, but it's quadratic in the density field. Okay. I also remind you that density is, the density operator is the Hermitian operator. Therefore, the corresponding field is real, it's not complex. This is rho of R. But when you go to Fourier space, it becomes complex because rho of Q is, okay, so this is another relation that we already saw a long time ago. Rho Q bar is rho of minus Q. Okay? And you can see it also, yeah, you can see it actually from this expression, you can trivially see it. Okay? Okay, so let us take the interaction to be this. Let's write it in this form. And now, what do you do with it? Okay, so let me suggest two ways to approach the problem. And we'll only follow the second one because it's more elegant in a sense. Okay, so let me erase all this. And so there are two ways to deal with S interaction different from zero. The first is, the most obvious thing is to do perturbation theory. Okay? Perturbation, but what we want to really do, and we can conveniently do in this functional integral formalism, is a perturbation series. So we don't need to stop at the first order. We can write an infinite series. If we are lucky, and in fact in this problem we are lucky, but it's a lot of work to show it. You can see that the higher order in the series give you a simple, you have to do some approximation, which gives you a geometric series, and a geometric series you can sum to all orders, okay? But I'm not going to focus on that. I have to choose my time. But let's just see what is the idea. How do you do a perturbation theory systematically? So just I'll give you the hint. So in principle, I have to solve a problem that is, I have in the exponent e to the minus s naught times e to the minus s interaction, okay? Right? Because s is s naught plus s interaction. Now, this one I can solve. So what do I do with the interaction? I replace it by power series, right? So any exponent can be written as an infinite sum of s to the power n, okay? And then what you'll discover is that you're going to get something like that. It's going to be a z naught times 1 plus s int plus 1/2 s int square, okay, something like that. And each of these terms we can compute because using the weak theorem, okay? okay? Because they're going to be just products of psi bars. We can use Wick's theorem, okay? So you can do it, and then you can take the log of this and get an expansion for the free energy to any order you like, okay? That's one way. Another way that we're going to do now, and it has some physical insight, it's not just a technique. This is called the Hubbard-Stratonovich. And this is what I'm going to now spend time on. Okay, so let's just leave okay, so I'm just writing actually on that as well. Already went through this, so I'm just writing S naught is, so first S is S naught plus S interaction. S naught is a sum over P and sigma of, P sigma minus I omega n plus psi of P, psi P sigma, and S interaction is this thing, so I'm copying it here. Rho Q, VQ, rho minus Q, okay? And just for completeness, let me remind that in our case, we want to have, this is just the definition of psi is epsilon minus E Fermi, where epsilon P is kinetic energy. And what else we need? Matsubara, we know, I'm not writing it again. And the Coulomb, okay, the interaction. So in principle, this is the Fourier transform of the interaction potential. In our case, for Coulomb, namely in real space, it's E squared over R. The Fourier transform in 3 dimensions is, okay, that's just doing the Fourier transform, okay? So notice that here I write it as Q vector square, so the when I write V of Q without the vector sign, Q corresponds, this is another notation that I'm reminding, that P is, and the same of course for Q. The interaction in principle, in a general theory, you can write an interaction term that also depends on the frequency. Okay, so it's when it's not static, when it's there is some time. So if there is an interaction that depends on time, not only on space, the Fourier transform will include some dependence on the frequency. Okay, but in our case, we just have the static Coulomb interaction. Okay, at least 2 leading orders or okay. Good. So, what I want to do now is introduce something that is called Hubbard-Stratonovich transformation. I hope we spelled it right. Maybe not. Okay. But Hubbard is the same Hubbard from the Hubbard model, same guy. And the trick is the following. So inside the partition function, we have an exponential of S naught plus S interaction, okay? And this exponential of the, so basically this exponential of S int is the complicated stuff, right? So instead of doing a perturbation expansion on it, let us introduce a formula for it. Because if we look at the form of S int, it appears as a quadratic expression in terms of the field O, right? Now, such a quadratic expression can be thought of a result of an integration. So I'm introducing here a step which looks like a complication of the problem. I define an auxiliary degree of freedom, okay? At the moment it's a mathematical trick, but it actually embeds some physics in it. So I write this as an integral over some other auxiliary complex field. I call it phi. It's a collective field. And this is what it is. So it's actually a Gaussian integral over this phi, which has the form, let me write it as, okay, this, and there is plus okay, something like that, okay. So such a Gaussian integral has an exact formula, okay. It's actually a generalization of a Gaussian integral that you are familiar with from a single variable thing, like e to the minus ax squared plus bx. So when there is, so what is, this is a Gaussian integral with a linear correction, which you can complete through a square, and then you can show there's an exact formula for it. Actually, let me be a little, yeah. Okay, let me write it. I want to be careful with the colors because so this all blue is an invented thing, and here I have rho dagger times phi. This combination is just to make it real, right? So it's, this is the conjugate of the complex conjugate of this term. And to be a little more careful, let me introduce here some parameter b, which we'll have to fix. Okay. I mean, I'll tell you immediately what it is exactly, but just let us write it as a general formula. This is just a Gaussian integral, which result gives you, if you do it carefully, it gives you okay, e to the, okay, sorry, there's, first of all, there is a determinant of, now I should stress that this phi is a complex field, not there's no Grassmann, okay? So all this Grassmannian thing is buried in the definition of the density, which you can write explicitly in terms of the fermions, but it's not useful for the moment. This is a complex field, and therefore
It is a scalar.
the integral, sorry? Yeah?
It is a scalar field?
Not a, no, it's not a, okay, scalar is another name for a real field. It's not real, it's complex. Okay, it's complex. Okay, so phi bar is not equal to phi. Okay, right. So, but the result of this is the determinant of v times an exponent. Because of the linear term, you get an exponent of, there is this parameter b squared, and then there is rho, sorry, let me write it like this, there's rho dagger, v rho, okay? That's the result of the integration. Okay, this is just a formula. Okay, so after you integrate over phi, this is the variable of integration, and you get something that depends on the density with some parameter that you have to adjust. It gives you b squared times v. And notice that if, because here I have v minus 1, you get here v. Okay, that's just usual Gaussian integral. Okay, now, what is this? First of all, I get a prefactor that does not depend on rho. So I don't really care what it is. It's just some number, okay? It's a normalization factor. And because it's a normalization factor, you can readjust the differential to absorb this factor so that you can define d as d twiddle, which is d times this determinant, and it gives you 1, okay? So this can be absorbed into the definition of d, so let's not worry about it. Okay? Then, if you do it like this, then I'm only left with the Gaussian expression. But the Gaussian expression is nothing but, it's something that is quadratic in rho. And it's actually exactly what we have, right? So this V matrix is in fact a diagonal. In our notation, it's a diagonal matrix with elements VQ up to some prefactor that settle the coefficient B. Okay? Okay, so now what did I gain? So I will immediately tell you what is the exact expression, but what did I gain by doing this? Okay, because it appears like I complicated my problem. I first had this is something I may want. So I remind you what I want to solve z, which is integral over the electrons of e to the minus s naught times e to the minus s naught. Now what I'm saying is, okay, let's leave this thing as it is. But instead of writing e to the minus s int, I'm writing it as another integral over something, okay? So it's another integral over this phi auxiliary field. It's like I introduced some external degree of freedom, but it's not really external because it's emergent from. So in fact, it's conceptually, where is it coming from? I'm actually reducing the interaction to something that couples through a mediating field. Okay, that's what I'm saying. The direct interaction, density between my particles is mediated by something that results from exchanging some gauge field. That's how you can think about it, okay? So now what do I have in this integral? I have, I have e to the minus, let me call it delta s, and this delta s depends on both psi and phi. Okay, it's a function of psi bar psi, but also it also depends on phi bar phi. Okay. So it depends on both of them. I have another integral to solve. What is the trick? Why did I do this? Because this delta s is the stuff that appears here, right? It's basically, okay, something, if I put here a minus sign, basically this is delta s, okay? And the thing is that the delta s is simple. It's simple in both phi and psi. Why? First of all, in the phi, it's quadratic, right? It's just a Gaussian plus a linear term. But it's also quadratic in psi, because it's linear in rho, and rho is quadratic in psi, right? So let me again write the definition. Rho of Q is the sum over P and sigma of psi bar P minus Q sigma psi P sigma, okay? Okay, so what I get is I now doubled my integrations, but all the stuff that I have in the exponent is quadratic in both psi and phi. Okay? Now, if I first integrate over phi, I go back to my original thing, and that's not useful. But I can say, okay, no, let us look at it differently. I first integrate over the electrons. And then I will get an effective action for this collective field that I denoted by phi. Okay? And this will give me insight. And I'll show you exactly what it gives. So, first of all, let me write this delta S explicitly. Or actually, okay, let me even do better. Now I need some space. Okay, I think this I can erase and I can rewrite it. So my S, I have an S which is a functional of two fields now. this one I want to keep the colors, just to keep track on everything that depends on phi. Okay. So what is it? First of all, it's S naught, which is just the free electron, plus a delta S. Well, and now what is the delta S? So I can, and delta S is the part that depends on phi and on the phi as well. And I can write this whole thing as follows. Let me write it. Okay, so there is a beta over here. I'm actually writing it already using the fact that this VQ is the Coulomb interaction, 4 pi E square over Q square. You can do the algebra and see that it comes out, but I already write the final result. So there is a part that only comes from the phi. It's coming. This is actually the Gaussian part, the quadratic part in phi. What before I called phi bar V inverse, etc. And here it has a very simple form here. There's a sum over Q, phi Q, Q square. Let me just check. Okay, it's fine. Phi minus Q, okay, plus now I have a term that is quadratic in the fermions, and it has the form of psi bar, psi dagger, because it's, I'm writing it here implicitly as a matrix, because it's so I can write it as G to the minus 1 psi, where this G depends on phi. Okay? It depends on the auxiliary field that I introduced. So I'm deliberately writing it like this. And notice that it's no longer G naught. It's G naught, so this G inverse is G inverse naught plus something. And the something is a linear coupling to the field phi. Okay, so let me write it down explicitly. What is G of phi? I'm writing it the G minus 1 of phi. I'm using the basis of states here is the Q, where Q is this Q or P, doesn't matter, it's a 4 vector thing. So let me write the matrix element PP prime. Okay? It's given by, first there is a diagonal part, which has just the G naught. That's G naught of P. Okay? Plus, this is the part where it couples to the field phi, and something that looks like E. E here is the electric charge divided by, let me just be careful about factors. Yeah, okay, you can write it like this. And then I have phi of p minus p prime. Okay? So let me explain what I write. Maybe this one
This
I
is
will.
rho, no?
This is, I'll write it with the color blue, okay? So this is, if you do the algebra, this is what you find. So the coefficient that comes in here now is not a diagonal matrix. It's not a diagonal matrix, okay? It has the free part, which is diagonal. That's why you have here the delta. But the second term, if you plug it in and write this term explicitly, you get something like, let me maybe write it. So you get something like, okay, let's take outside this factor of E omega. Then I have a sum over P and P prime of psi, and of course there are the sigmas. There is the sigma. So psi bar P sigma, phi of P minus P prime, psi P prime sigma, okay? And there's summation over two indices. It's not diagonal, okay? Actually, if you rewrite it, so this is like, notice that what I got here is something that looks like free fermions, but which has the part coming from the kinetic energy, right? This, just to remind, what is this? This is a minus I omega n plus xi of p, right? This is what it is, just a kinetic part. But then there is a linear coupling. Notice that what I wrote here can be thought of as linear coupling of the density operator to some field, okay? And if we turn a blind eye to the fact that there's a factor I here, so it's imaginary, it looks very much like coupling of density to some field. Let me write it in real space, and it will immediately give something nice physically. Let me erase this. And I just want to note here that Z naught is, okay, actually I don't need it. No, we have the formula if we need it. So if I'm converting this effective action, okay, to real space, going back, doing the Fourier transform. And when I say real space, it's space and time, space and imaginary time. I'm going to get the following expression. With your permission, I'm erasing this. And writing the result. So there's an integral d tau from 0 to beta, integral over space of, first there is a term that comes only from the phi alone, right? And if there's a q vector square, it's the gradient, okay? So there is a term that looks like 1 over 8 pi grad phi absolute value square, okay? Actually, let me write this in blue. color. Okay, blue. This is just this part. Plus the free fermion part, which I'm now writing as a sum over sigma. Then still the spin index appears in a trivial manner. There's a psi sigma bar, where this psi is psi of r and tau, right? And then what I have here is the tau plus the kinetic energy is grad square over 2m. This is just the kinetic energy minus mu, right? And here comes the important part, plus IE times phi of r tau. Okay, that's the auxiliary field that I'm coupling to. And this again is multiplied by psi r of r tau. Okay? This is how the action looks in real space. Let us stare at it and try to figure out what kind of physics it describes. Okay. Now what do we have here? Okay, and again, as I said, if you take, this is the action that you have to integrate over, but you have to do a double integral, and you have a choice of first doing the electron integral and then remain with a theory for the effective theory for the collective field. Okay, so we basically, what is the idea? I replace the individual particles by a collective field. Okay, a collective degree of freedom. Now, what is the physical interpretation of this? If you look at the first term, the term that just depends on this auxiliary field. What does it remind you?
It's the wave equation.
It's not an wave.
Well, it's not the wave, but
an
it's the
equation.
It's the action of the wave. It's the Lagrangian of a wave equation that gives us
That
equation.
right? It's or at least one term of it. It's actually, if you can think of phi as some kind of an electrostatic potential, quote, then grad phi is electric field. So the first term is just E squared over 8 pi. This is the electromagnetic or the electrostatic part of the electromagnetic interaction, okay? So there is really a feeling that indeed this auxiliary field is a kind of a gauge field, okay? It's some kind of electromagnetic, emergent electromagnetic field. And that's actually true. That's the photon that we're talking about is carried by this field. Now, the fermions are coupling to this field, and this again it looks like a coupling to an electrostatic potential. With one caution about the interpretation, there's a factor of I. The factor of I is actually very important because then in the Gaussian integral you want to get e to the minus something positive, right? To get a well-defined theory, okay? So it's kind of a gauge field, okay? Kind of. It's not electrostatic actually, but that's what it is. That's the intuition behind it, okay? And again, if you would integrate over phi, it will just give you back the interacting electrons, and it is really what this this diagram is all about, right? So the collision between two particles interpreted as there's some exchange field between, some exchange photon between them. It's a mediator. Okay. But the trick is we are not going to integrate over the field and go back to the same problem, because then it's very nice to write it, but we didn't solve anything, right? Instead, we first integrate the fermions. And we can do it because it's a quadratic action, okay? So, and we know the solution. We know that, so let me rewrite it. I want to say that the action Z is going to be an integral d phi bar phi of e to the minus something that I will call S effective of phi. Okay? Now let's see what is this S effective. Okay, so S effective, so e to the minus S effective is given by integral over the fermions of e to the minus there is a prefactor that is only dependent on phi, so it is e to the minus beta over 8 pi omega, sum over q phi q. Okay, I'm actually going back to K-space because then the integration over fermions is easier in K-space because it's diagonal in K-space, not in okay, it's not exactly diagonal because the correction from the phi is in momentum space is non-local, it's not diagonal, but this is the thing, we can maybe expand it if we like, so we'll maybe soon get to it, but let me first write an exact expression, okay? So e to the minus S effective has a trivial Gaussian factor, but then it's multiplied by something that comes from an integration of e to the minus a quadratic action g of and this g contains a dependence on phi, okay? But by itself it's just a matrix, okay? It's a matrix that couples quadratically the fermions, and we know to solve this integral, right? So what is this? It is, because there are fermions, besides fermions, it's the determinant of this exact same g to the minus 1. That's all. Okay? That's what it is. Which is a functional of, it's a functional of phi. Okay? That's what it is. Okay, but then, okay, so this is an expression. This times the Gaussian factor gives me e to the minus S effective. But now I want to derive what is S effective itself. What is S effective itself is if I write everything here as an exponent, this is going to be my S effective, right? Or minus S effective, right? Now what is this? This is not written as an exponential of something. It's a determinant of a matrix. First of all, it's a number, right? It's a scalar number, so, but I can rewrite it as exponential of a log, right? So it's an e to the log of or ln of that g to the minus
log.
what?
Minus log.
Actually, yeah, so
That would
as
be useful
I
to
wrote it here, it's an exact thing, but if I want to write it as e to the minus something, you're right, I have a minus sign, right? So one has to be careful, but now,
matrix, it would
Yes.
make it actually much easier.
sorry?
That would convert the matrix of the Gaussian integral.
Yeah, so this will give me, so what I'm getting, let me just write down the final result. Let me just use here one color because we got rid of our, sort of got rid of our fermions. So what is this S effective? It's going to be beta over 8 pi omega sum over q, phi q square phi minus q. That's the Gaussian part. Plus, now minus ln of the determinant. Ln of that of g minus 1. Okay. Now there is a mathematical identity, a general mathematical identity that you can prove very easily. I think you may even have your homework, but it's really one line of proof that a ln of a determinant of a matrix, okay, is equal to a trace of the ln of the matrix. Okay, this is just a mathematical formula for any matrix. Okay. Why is it useful to write it like this? Because first of all, a ln of a matrix is a very convenient function to expand in a power series if you like to do some approximation. And then the trace is just sum over the quantum numbers, right? So it's sum over. So by the way, because so A is a matrix, is log of A is also a matrix. Okay, and it's defined by the power series of the function log. Okay. So it is some complicated, in general it's a complicated matrix, and but you can write it like this, and then I have a closed expression for the collective field, okay? So because I don't have a lot of time, I want to get to the punchline. I'm not doing any algebra, I'm just telling you the result. So let's explore what is going on here. First, I already showed you the first term in terms of the collective field is trivial. It describes free waves, right? It's exactly what you have in the Lagrangian of electromagnetism that we discussed in the beginning of the course. But then there is a correction, and this correction that comes after integrating the fermions. Okay, we are exchanging the order. We treat the electron system as some kind of a medium that feeds into our collective field. And this introduces some nonlinear correction, some quartic and sixth order. It gives you an expression that actually for symmetry reasons you can show that it must contain only even powers of phi, but it's still an interacting problem, so it looks like you didn't solve much. But here's the point that you might want to do an approximation. And the approximation is you have to solve an integral over, eventually you want to solve an integral, a path integral. And in the exponent you have a function that in some regime that we are interested in has a small parameter, actually a large parameter, okay? So in particular, notice that up front here, there is a factor of beta. Beta is the inverse temperature. If we're interested in low temperatures, or even in the limit of zero temperature, which is actually the ground state of the system, then beta is diverging to infinity. But for any small but finite temperature, we can treat it as a large parameter that controls the size of the exponential, and then we can do a saddle point approximation. If you do the leading order in saddle point, you'll discover that it gives you back the Hartree fork, okay? The mean field. So the mean field is in fact the saddle point approximation of such a theory. But the next order, which is going to be second order in phi, why second order? Because the first order vanishes by symmetry, right? And actually the saddle point of this, the saddle point solution for phi gives you phi equals 0. Okay, so there is no contribution. This is the only solution, but the second order will give you a correction which is again quadratic in phi. Okay? And let me tell you what it is. So what you're going to find, now I erase all this, forgot about our electrons. Let us just look at the collective field. What does it do? And you will get that S effective is, now I'm writing it, it's a function of phi, okay? So there's a factor of beta over 2 omega. This is just 3 factor times sigma sum over q, where q is again our omega n and q vector, 4 vector, and then we have phi q n times dq phi minus q. But what is this d? What is this d? It's given by q vector square over 8 pi. This is the what you get from the Bayer theory. Actually, no, sorry, it's 4 because the factor of half I took out. So it's q square over 4 pi. And then minus e square pi q, where pi q, I can write it as a formula, but I'll tell you what it is. What is it?
Variation of the action.
So no, so what pi, this pi, and I denote it by pi, is the polarizability of the electronic system, okay? Which is related to the dielectric function, right? So when you have charged particle, a plasma of charged particle, this is what the electron system is. It's a plasma of charged particles. And when you put an electric field in it or some electromagnetic field, it couples to it and creates dipole moments, right? With some susceptibility, and the coefficient that relates the polarizability or the electric polarization of the medium to the field is called polarizability, okay? Yeah, so in fact, you know what, I'm not even writing, let me just write it down. I'm not showing where it comes from. This is just what it is in terms of the Green's functions of, so it's G, P, plus Q, okay? So pi of Q is, if you take the Green's function of the non-interacting particle, right? GP naught is 1 over minus omega n plus xi p vector. This is what it is, right? So when you take the summation over this, you get something. Now, what is the physical interpretation of this something? It's when you have an electric field EQ multiplied by pi q gives you a dipole field, okay? So that's what comes into the dielectric response of a function. Now, if you look at this, so this is d of q, and if we recall, what is this q square over 4 pi? It's up to a factor of e square. It's nothing but the inverse of the Coulomb interaction, right? The Coulomb interaction was, this is V of Q, is the inverse of this, and there's some factor of e square, right? So, sorry, there is an important, sorry. I want to call this the inverse. Why? Because then in this form, what I got is a free theory for phi, right? It's a free theory for phi, where dq is the Green's function of the collective field, okay? Just as we learned in general, so this d of q, dq is by definition phi q, phi minus q, okay? This is what it is. It's it's the Green's function of the field, but in the action, you always get the Green's function to the minus 1. So that's why I define it to be d to the minus 1. Okay, sorry about that. But then if it's if this is d to the minus 1 and it's in a diagonal basis, what is dq itself? 1 over this, right? Okay, so let's write it down. So dq, if I invert this function, I get something that I can write as follows. Let me just be careful with the there's okay. Write it like this. This is true up to a factor of e square, I think. Let me just forget about this factor. So let's assume that e is also 1. Okay. Okay. So one has to be a little careful here. Anyway, what you get is that it's actually v of q divided by a correction, which is No, let me bring back the unit. Sorry for being a little sloppy. I write it like this. 1 minus pi q vq. And then, so the e square is okay because it appears here. Okay. All right. What did I write here? You see that if I didn't have the electrons, if I had this collective field would live in a vacuum, I will just get VQ. So VQ is in fact a propagator of a photon, which is the field associated with electromagnetic field. Okay. Just as we kept saying about this diagram, okay? But because of the coupling to the electrons, I have a correction. There is a denominator, right? So I can write this as VQ over E squared times some epsilon of Q, and epsilon Q is this stuff, which if you do the calculation carefully, you can see it gives a positive function actually. But it's actually not necessarily, because Q here also has frequency, and you have to be careful, but in any case, the physical interpretation is a dielectric function, okay? And what did we learn from it? That when you put, let's say that this auxiliary field was some external field phi, you put it in a medium of charged particles, the charged particles interact with it. If you integrate over them, what do? They give you a dielectric response, and this is nothing but a dielectric factor. Okay, it's not a dielectric constant because it depends on Q, and it depends on Q in such a way that for some so generally in a metal, just at low frequencies, it just gives you screening. It screens the external potential, and it actually tells you that the effective interactions that the electrons really feel are screened by themselves, by their friends, their neighbors, right? And that's why, and this epsilon at small q, small momentum and small energy is actually diverging. Okay, so because it's diverging, the screened potential is very small. Okay, so even though the Coulomb interaction is huge, or not huge, it's big scale, it's comparable to the kinetic energy, this captures the screening effect. Okay, and it's reduced. So that's one thing that actually justifies our mean field, right? Because we can say, okay, we did work very hard, but then we actually discover that the second order corrections and all these complications are just justifying our original assumption. Okay? And all you need to do a decent calculation is replace VQ by VQ over epsilon, the screened potential. Okay? The second observation that is very interesting, actually this epsilon of Q, which is a function of frequency and wave vector, it has a resonance in some particular Q. Okay, so there is a particular value of Q where this denominator vanishes. Okay, when it vanishes, you get, what does it mean that it vanishes? It means in that limit, it's exactly the opposite of what I said. You get a divergence of the interaction potential, so something singular happens. Now, what is this collective mode? So it actually suggests that there is a particular frequency and wave vector in which you excite some collective excitation, and this collective, if you convert it to real frequencies and all that, you find something that is called the plasmon, which I think you've seen in your wave theory course. It's plasma oscillations. Okay, remember you learned it? You know what is the plasma?
Plasmons.
The plasmon, okay? So there is a mode that obeys, there's a plasma frequency plus something times q square, right?
So debate frequency. Debate frequency.
No, it's not the bi, it's so the plasma frequency for metals is 4 pi n. I mean, this is something you are supposed to learn. Okay, I think this is actually omega p square. You saw this? Plasma frequency from undergraduate.
I didn't remember this as the expression, but yes.
Yeah, this is the density of charged particles and the mass, okay? It's called the plasma frequency. So it has a dispersion relation with a threshold, which is the plasma frequency. At least this is what you find in 3 dimensions. So all of this is actually, all this physics is embedded in this effective action. So basically what I'm saying is that forget about your electronic systems. Right? The most important degree of freedom here is the collective one. But if you are really at very low frequencies, below the plasma frequency, the plasma frequency, by the way, is again very large. It's like comparable to the Fermi energy in metals. But if you go below it and you don't excite this mode, you just have screening, and the Coulomb interaction is screened, and the free electron description of metals is recovered. Okay, that's the message. Okay, but you can get so much more from it. Okay. Okay, so I think sorry for taking a little more time, but I just wanted to finish it because next week. It will be an enrichment program, and I'll teach you a crash course on the Dirac equation. Okay? Okay, so thank you for listening.
תרגול.
Okay.
I see that we don't have a lot of people, so it'll probably go quicker. Just so you can just stop me whenever I go and ask me a question, I'll just run over the material. Yeah, okay, so today we're going to do a few things. We're going to talk a little bit about field integral, but just a short summation on how to solve them. Honestly, this is the material that looks the scariest in the course, and it's the easiest. There's one method to solve it. You just do it like you throw your head in the wall, and that's it. And after that, you just 2 of you here, so probably also publish like a question in the website about when we're gonna do the tutorial and what sort of materials you want me to upload. But this can wait till the end.
There is a homework for this.
Yes,
tutorial.
there is a homework.
Yeah.
I should have. Usually, I ask Fred if you want this to be like you have to submit it or not, or if it's just for you. And I will upload it anyway, and then the worst case scenario, you should do it because there's all important stuff there. Exam and stuff, yeah, there's a lot of good introductory material. Here we're gonna do just a very simple question, but I know it will be a bit more complex. And also here we're just gonna touch on how to do all this stuff with fermion, and in the homework you'll see it more explicitly how to work with fermions. So you should do it anyways, the homework that will be uploaded. Let's see if there's any other small announcement. Just some test stuff, but I think I'll just upload it. Let's upload a message on the board and be more effective. Okay. So I'm not gonna do the entire spiel of how we connect coherent state into field integral, because I'm sure Efrat told you about it, but I will mention it. Bosonic coherent state, defined as E sub I dagger 0, right? And fermionic, mu equals E I.
The 0 here is the Fock state, right?
Yeah, it's the Fock state 0.
And eta is
Eta
Grassmannian, right?
Yeah, it's a Grassmann variable, which we'll talk about it again in the end of the lecture. And the reason I want to bring it up, even though we're not going to really talk deeply about it, is because specifically for the bosonic case, which we'll see it a little bit more, there's two other representations which I really wanted to give to you because you'll probably see them sometime in your work university. First of all, this is the representation that I usually encounter, which is the explicit quantum state representation. So you can see this is just an explicit field. You don't have any operator in the exponent, stuff like that. And you'll see it, for example, when you want to calculate some like quadratures and some other qualities of state, it will be easier to operate like this. And the second one, it's very similar to the first one. It's actually the more complete and more accurate one. This is the representation that you usually see when you try to explore time development of states or operators using Hamiltonians or whatever. Yeah. Okay. So, coherent state, some lecture material, not tutorial material, and then we go into field integrals. Yeah, amazing. So the entire subject of field integral is solving a very, very specific problem, trying to find the partition function, which I'm sure you also, all of you are taking advanced statistics.
Yeah, we don't really cover, but we all remember from statistical mechanics.
Oh, you don't cover? You don't have
We weren't
partition
doing
function?
field theory, right?
Yeah.
We weren't doing
Ginsburg-Landau.
Oh, I heard that the course changed. I didn't know that much.
Yeah, now we're doing renormalization, so we're more doing like
Oh. Okay, but you
we
understand
did
partition
statistical
function.
mechanics. We did
Yeah.
statistical
All right.
mechanics, so yeah.
So this partition function is is the same, just a little bit weird. A little bit weirder. Note that instead of having a phi and nu, I always forget eta. I always forget the name of this character. I'm just gonna write psi as a general case. E minus S conjugate, where S is the action. Which most generally will look like so. There's a beginning and an end. Okay. Mu n. Yeah, which of course H is the Hamiltonian, N is the number operator for field. Okay.
Is that what's? Oh, that's mu.
Mu. Yeah. Right. Now, this is not a big deal. This kind of look like a big deal, and it's. I don't know any method to directly calculate this kind of integrals, but it's an integral over functions. Similar to what we did last tutorial in the path integral, field integral also works with some weird integration of the general function that it can be. And now we see that we also have another complication here, that we have some integral over function. I'm just going to stay consistent. Over some function in the exponent which has some derivatives and annoying stuff in there, so we can't directly use stuff like Gaussian integrals. Which Gaussian integrals is a good answer to a problem that looks like this because they're consistent even when we integrate over a function over numbers, even when we integrate over Grossman variable, although there's an easier method of Grossman variable which we'll see in the end. So to solve this annoyance, we go to the savior, our savior in mathematics, Fourier. I don't know where we'll be without him today. And say that each function, if let's say this is a series made from a series of different functions, each function I can take to transform over beta. So n Vn I e minus I by n tau, where of course Vn I is just Vi complex conjugate over again. Basically, just the simplest, just the oldest trick in the book. Don't like a function, there's a lot of derivative stuff in there. Just move it into the Fourier space, and we all know that what happens when we move to the Fourier space. The derivative just become constant. It's much simpler. Now, this is trick number 1 that you need in order to solve this kind of question. Trick number 2 is again a trick that you saw, just remembering the integral where 0 to beta d tau variable beta e to the minus I over n minus over m tau equals delta over n over n. And that's it. You can go home. This is basically the chapter. Just do this. Know how to do Fourier transform. Maybe a little bit more complicated function than just a single derivative. Be consistent with your math. And this is like a third of the test guaranteed. Right. So now I gave you a lot of mathematical background. Let's do an example. The example that I want to do is non-interacting Bose gas. The most basic example that I can think of. I go back to question. I go back to phi because we're talking about bosons. Equals sum over k. Okay. Note that in order to translate our function into field integral, I just replaced the operators with field functions, the non-field functions. All right. So our action would be sum over k. Integration dt d tau is equal to b of e conjugate k tau on the right of tau tau phi of k plus epsilon k phi k minus mu k. Because of course the number operator is just a dagger a, so in our case it's phi conjugate phi. Alright. Doing a Fourier transform to all of this will give us the sum over k and then 2 distinct sum, one sum over every function here, sum over k and m of n k conjugate minus I omega n k plus epsilon k conjugate mk minus mu phi mk conjugate phi mk. Right? All this will still have the integral here. The integral doesn't disappear, but I just removed all the terms that depend on tau, the outside. Beta here is from the normalization factor. And all right, I'm gonna finish writing this line down and say something. The thing that I wanted to say is that many times when I write solution to test problem, which again this is something that I'll upload to the website, sometimes I neglect this normalization factor. Please be better than me. All right, please be a better person. Although as far as this is not something that you can take to the test, and to the FAT A, so I told you, usually FAT doesn't really care about the constant. I also don't think it's a big deal, but be better. So this is delta, of course, and this delta means that n equals m, and I can combine all these terms into a simple sum over n, sum over k, phi k minus I omega n, sum k minus mu p and k. All right. Note that while k is the wave number and n represents frequency and they're sort of related, they're not the same sum. Those two sums are independent, even though they describe two properties that are somewhat related to one another. Just totally confusion. Alright, so now z, the partition function, would be integrate over the phi e to the minus k and plus okay, so I'll give you 3 guesses how we solve this. And I am so sure of you that I don't even have the solution in my notebooks.
Well, first you can just separate the solutions for every n and k, basically. You can easily turn it to a multiple of exponents, and you just only have to do it
for each one.
and then you just have to solve it once, and then just do. Basically, you only have to solve it once.
This is
Ignore the problem.
this is just a Gaussian integral that you saw in your last homework, and it's even easier because all the terms are all the diagonal. You don't even have to find the determinant, right? So yes, congratulations, you solved the field integral question. And what can we do with this? Well, as with every partition function, we can use it to find properties of the field that we're interested in. For example, if I have some sort of operator f, we all know that the expectation value of f will be 1 over z, 1 over the partition function, d phi f. Of course, when I write f with a hat, in the integral, it's not literally an operator, it's some function that depends on the wave, in the field, either the minus s. It's very useful. Right. Now, so let's try to use this to find some property of the non-interacting boson gas. For example, the number operator. It's the expectation value of n. Well, we saw that it's easier to work in the Fourier space. So I'll do two steps. First of all, open it to sum over k, because our initial equation was also defined by sum over k, and also open it in the Fourier space. One over beta, sum over n, sum over k, 3k. Alright, so what we need to do is just find this one and sum over it. So I'm changing the indexes here for nq because in the exponent we have an nk already. Great. Q. Q. E minus omega of phi. Okay, conjugate. And I think any of you are like really astute, really sharp, note that you saw this in your homework as well. And for general Gauss, I'm just going to remind us for the Gaussian term, for the Gaussian integral, and it's equal to just the nm term. So it's easy to see that this term q q will just be equal to 1 over minus I omega m plus epsilon q minus mu. And after this line, I'm going to return to nk. Yes, question?
Okay, so we didn't explicitly calculate the integral of the partition function because we had no point of doing that, right?
Yeah. I just skipped this.
It wasn't the question.
Yeah, it wasn't.
Okay.
It was the question. B, this is way less interesting than what's about to come.
Okay. Great.
Yeah. All right. So
now we have to plug it back into the n.
yeah. Now I have to plug it back in and get. It's again gonna be like a two-step part. I'm first of all gonna. First of all, gonna calculate the sum over n, and then we'll see. If you're left, I'm actually gonna add something to the tutorial in a second after we finish with this question, because I think it's important. So, this one, sum over n, t, which t is just 1 over beta, same as thermodynamic. Right? 1 over n plus k minus mu. And now, what the heck is the answer for this summation? Well, I'll solve it in a method that's called Mitsubara summation. Basically, what I'm going to do is I'm going to try to find the integrate that's equal to this sum that we cannot solve, and on the other side equal to something that we can actually solve. This is the short version. So now for the full version, I'm going to define a function h of omega n equals minus t I omega n minus c. So this is just basically like taking a single term from this summation. And if we'll sum over n, done. Right. Now I'm going to define another function to help us. G z equals beta divided by e beta z minus 1. Okay. The next step is going to seem a little bit arbitrary, but I'm going to define an integral over English of a counter in the imaginary space C of z gz h minus iz. Right? Let me just draw the contour. Let's do it over there. Bye-bye. All right, if this is
Oh, okay. There are two residues.
Hmm?
There are two residues.
You need to be slower. I'm not as fast as you. Yeah, but you're right. The two
I
residents.
deal a lot with winding numbers, so like I'm just like that's my research is very big on winding numbers, so it's just like.
Oh, so you'll
So I
you
just
know
see
this
it
method. So did you see
No, I
this
don't.
method in the past?
I'm in solid state. I'm just like so used to it, like already now. Like I see like a contour. I'm like, what's the winding number?
Good to see that somebody uses this method of solid discourse because I didn't see it actually.
Yeah,
That's how
I'm in
you-
Balakai's group, so we use Z transforms a lot, so that's why I recognize it. That form very.
My contour is basically like a big ellipse to encompass all the imaginary, line, and we'll see that we have one second. We have many poles along the imaginary line from here from here. Yes, of which z equals to I omega n. Why is that? Because our frequencies in the Fourier transform are defined by some full parts of 1 over beta. Omega n equal to 1 over beta to pi n. So whenever we input z equal I omega n, this exponent will be equal to some I times 2 pi n minus 1, so it's 0. So this is a pole. So we can calculate this integral using the residue theorem. So the residue theorem tells us that if we have a contour integral, it equals to the number to 2 pi I sum over the residue, which we'll talk about what is it in a second, jz h minus iz, right? And the residue of this gz h iz is defined as z minus I omega n over I z minus I omega n times g I omega n h of omega n. Yeah. Right. This is the definition of the residue. Of course, no, technically it should be z minus iz at z equal. It's more accurate.
Well, well, no, but then you still have the singularity for g of z. And you replace that with the beta, wouldn't you?
Let's see what will happen. When we do a symbol like this, we can exchange it for a limit, approximate it for a limit, and we'll get lim z go to n. I'm just taking these two parts because the h will not zero out, I know that. It will be beta z minus I omega n divided by e beta z minus 1. Now we can use L'Hopital to take the derivative of both sides. Lim go to I n beta 1 divided by beta e beta z equal to 1. So this entire residue, where's this line? Entire residue is equal to h omega n. And now we'll note that since we have a pole at every one of those omega I omega n across the imaginary line, this integral will just be equal. We just write it again here. 0 c dz gz h minus I z equal sum over n h omega n, which is exactly what we want. This is one side. This means that this integral is equal to this sum, up to putting the c inside. You got any question for this transition? Because it's a little bit complicated. Questions? All right. So this is one side. Now we need to do the other side. The side that we actually calculate what this integral will equals. So we'll note that we have another another point, another pole in this graph, where z equals c. Why? Because when z equals c, we get h of minus I c, minus I times I is 1, c minus c, infinity.
But we just contour less than that, I assume.
Yeah. The best, you can skip for it right here. Usually what we do just to visualize it better, imagine instead of an infinite ellipse, I draw a circle around everything, and then when I expand the circle, for example this circle, I intentionally leave this point out. Then I expand it all the way to infinity, and we can use again the residue theorem. But this time, we have a point on the outside, so we just take the residue theorem on that point in negative. So on the other side, this integral, just write it here. So, well, 2 minus 2 pi I res of g z h minus I z equals c, which equals 2 pi I, already remove the minus in advance, z minus c, e beta z minus 1 here, z minus c at z equals c, just be equal to 2 pi I divided by e beta c minus 1. So nk equals sum over n h omega n equals 1 divided by e beta. Now I'm gonna put the c back in. C is mu epsilon k minus mu minus 1. We're done. That's it. That's it for this question. So, you have any questions before we do like two final things? Oh, wait, we are going to finish early. What? Okay. I was just going over this. This method is not that complicated, but remember it might be a bit. So it's just going over it once before the test. Even though I think I only saw it 2 times, the test that I found this course. So, yeah. So again, to solve this kind of questions, you need to know how to do the Fourier transform. And when I mean know how to do Fourier transform, you don't just do the transformation itself. I also very much recommend going over Fourier rules. For example, if phi is even let's go real. Let's see there. If phi is real, phi Fourier transform of omega is equal to phi minus omega conjugate. I hope I don't confuse it with the if phi is fully imaginary. For example, this kind of rules. I definitely recommend you remembering these rules because they will show up in the test. You will need them. Most questions I saw in the test require you to will be much easier if you remember the Fourier rules. The small group. There's not a lot of them, but you should go over them. Second of all, go to the last homework. Look at Gaussian at the result, the equation of Gaussian integrals. And the test has, if I remember correctly, there's an open material. Pretty sure. kind of forgot actually, which is a little bit embarrassing. But I'm pretty sure it has an open material, and if it does have an open material, just sum the all like last. Just take the last homework. You don't even need the answer because the last homework already has the all the cheats in it.
Oh. So basically, we said that the sum of all the residues is 0, so it's negative the residue at z equals c,
The sum of all the residues,
including z equals c,
yeah.
equals 0. Okay.
Yeah, basically you can also, if you want to do like the real math reason why it's equal to minus 2 pi I is because going counterclockwise, it's basically counting all the point inside, and going counterclockwise, going clockwise counts all the point outside.
Okay, yeah, no.
So again. But it's the same, yeah, what you said is also the same. So yeah, just it's very important to me to make it clear that you just need the three different 3 points, 2 points. I don't know if you want to combine the integral of frequency difference equals delta as another point. But anyway, just Fourier and Gaussian integral is enough to solve this kind of questions. Now, very shortly, I'm going to talk a little bit about the Grassmann variable and Grassmann integral. Grassmann-Gaussian integral. Very brief. Now, Grassmann variables are just wacky numbers, really weird quote-unquote numbers that satisfy a very simple condition. And eta?
Eta.
Got it right. Eta I, eta j equals minus eta j, eta I. So, similar to how you do with the fermionic operators. Another important note about them is that eta I equals to 0. I think it's pretty self-explanatory why line 1 infers line 2, because if you switch them around, you get the minus sign, and if a number equals the minus of itself, it must be the 0 number. Because this is a real group, and since ni squared is equal to 0, this gives us a very easy Fourier transform, not Fourier, Taylor expansion, some function of eta, for example, in one dimension, equal to f0 plus tag 0 times eta, and that's it. So it's
Also, integrals are easier.
very much so. Very much so. There are 2 rules for integral, but we'll get jumping ahead.
2 rules.
There's basically 2 rules for integral and Grassmann variables.
We just say like the integral is the derivative, if I remember correctly.
You'll see in a second. Now, we can also expand this rule to how many dimensions that you want, but I'm just going to do 2. So if you have f of, let's say, eta line equal to f0 plus d eta f0 eta plus d f00 plus 1 over 2 d eta eta 0. And I'm going to write this one here. Note that there are two second derivative terms. Since the order matters, we have derivative in one and then the other, and then the
Shouldn't they cancel out? Or
no, note that replacing these two will effectively give you a minus, and replacing these two will affect. Okay, they won't precisely give you a minus, but something similar to a minus, and then replacing this one will give you a minus. They don't cancel each other out. For example, just look at d to I to j to I. This one will be equal to minus to j. The I to j will be to j. So there is a meaning for both the order of the Grassmann variable and the order of the derivatives. So if they won't cancel out, they will also they're not also not equal. Also, again, note that we don't have second derivative of any one variable. I wanted to say something else here, but I don't know. If I forgot, it's probably not important. Right. So this makes our job with the Gaussian integral much simpler, because minus eta a eta. Note that a is just a normal number. You can combine numbers and Grassmann variables in the same equation. Equal to 1 minus eta a eta. I forgot the conjugate here somewhere. This is here. This makes everything so much simpler. So let's use this. And wait for that. Two more rules. Integral, Grassmann integral over nothing, number 1 will equal to 0. The Grassmann integral over Grassmann variable is equal to 1. Yes.
that doesn't feel right.
It's weird, but it is what it is.
Because it should be eta squared, and eta squared is equal to 0. So
Right. Well, yeah, it seems like it, but Grassmann variable doesn't really work like normal numbers. If you're interested,
yeah, like it's
you
just
hate it?
everything in
It's
my
weird.
body
It's
screams.
Fermions are weird.
No, but like some of the things are weird, but you're like, okay, it's weird, but I accept it. This is just like my body screams. Like based on that, the fact that eta squared equals 0.
Eta squared equals 0. Yeah.
Logically speaking, it just like it has its own math.
Yeah, like even the integrals though are just a different math, and that's what's annoying.
Yeah, it is because it's defined differently. But the thing is, we are trying to make it work with.
This is. I wish I had it written down, because now I don't remember exactly the definition of this group, because you can define this group using matrix, and when you define this group using matrix it makes a little bit more sense, but still I didn't dive too deep into why it works.
It must be because, as far as I know, there is interaction between bosons and fermions in nature.
Yeah.
So if it's so, there must be a common math.
Yeah.
Like we must be able to describe it in.
Yeah, which is there's a few ways to describe this coin. I don't want to go into this.
Okay.
They're just weird. They're not numbers. They're something else. They're like weird creatures. They do whatever they want, and we don't question it. I'll try to find if I can like upload something to this about specifically like this line to the website. But if I'll find it and it's too complicated, I'll just give up, because you don't need to know it. You have a test on your head. You don't need this random math. Some crazy mathematician came up with weird numbers, and decided we all have to deal with it. Anyways, so now to do a Gaussian integral in one space, in 1D, would be relatively simple, even though those numbers are weird. Minus equals well, the one is actually a 0. Don't believe it. It's a 0. And now minus a is a normal number, so I'm just gonna take it out. Right. Now what I'm gonna do is I'm gonna flip this to Grossman variable. I'm just gonna do this. Right. Then I'm gonna add a little parentheses here. It's a group. It's a full. I think it's actually a field mathematically, but I'm not gonna be such a stickler. So this one is a 1, and then this one again is another 1, and we get a. That's crazy. Okay. Now for the multidimensional case. Multidimensional. Eta. Note that these etas represent a vector. I'm gonna write it like so it will be clear that it's a vector. I want to say that this one is equal to the that A. Alright, how do we do this? Well, just go one by one. D, eta 1, D, eta 2, and so forth. E, the minus sum over I, J, N, I, Aij, eta j. And similar to what you did with normal regular numbers in Gaussian integral, we do here with Grossman variables, which is, I'm just gonna do a unitary transformation over the eta. I'm gonna say j dagger is equal to let's do a different one, not phi. Let's do a theta. Sum over L, not phi, theta L, conjugate U, ULI, conjugate eta I equal sum over k uj k k so I, where the u will be unitary matrices, which u diagonal a u equals some diagonal matrix. So overall, our integral, let's give it a name. Let's call it I. So our integral I would be equal to integral theta 1, theta 2. Note that since our transformation is based on unitary transformation here, and the unitary transformation Jacobian is 1, we can just replace the integrates here directly. E the minus sum over I, j, k, l, theta, l, u, l, I, diagram, I, j, u, j, k, k. And we'll note that sum over ij of u, l, I, a, I, j, u, k, j, k will be equal to d, l, k times delta l, k. Since we define it as it's a unitary transformation to a diagonal matrix. So this is basically just this line. Right. So we'll get that I equals again the integral theta 1, d theta 2, so forth. E to the minus sum over the k equals 1 theta k d k theta k. This will be equal. If again we'll do every one of this term one by one, equal to 1 to n of the one dimensional sum over k d k k, which is of course that d, which is of course that a. Whoosh. Basically. All right. Now I'm not going to prove this following formulas. You can try to do it yourself, but it's basically going to be the same as your homework, just following the rule of the Grossman variables like we did here. But I still want to give them to you. First of all, they're very useful, as we saw before, fully dimensional with sources, fully dimensional Gaussian integral with sources. Plus theta u plus u delta v equals that a times e v dagger minus v, and the expectation value I equals 1 over a and j u j I. There's conjugate on the I. Equal a minus 1 ji. Ji times a minus 1. Okay, we're basically done. I will suggest reading the Bose-Einstein condensation at home, although the homework are much more important. The homework are much better. And I think I said everything I want to say about the test. If you have questions, you can ask. Questions that you can ask. As far as I'm aware, same as every year, the test will be. I didn't see it yet, so I can't be 100% sure. But usually, the test is 3 questions always the same 3 subjects. You can look them up in the past test. One of them will be field integral, one of them will be BCS, something like that, something where you have to open a complex Hamiltonian. And the first one will be something that's required to Lagrangian mechanic, usually. But again, just open the test, like the past tests. I'll also upload them, whatever I have, into the website, and later I'll also upload all my solutions, which is basically all the tests. And you'll see that they're always the same 3 questions, same 3 types of question.
Topics.
What?
Same for 3 topics.
Same 3 topics. Although Efrat's a can, she know how to like make the question diverse enough, so we need to understand the material. And of course, when we do the tutorial before the test, we'll go over every question, how to approach it, all the methods and tricks, and you'll see that's almost like everything in quantum mechanics is just calculating ahead, just doing the very repetitive actions. That's it. I definitely say it with full confidence that you shouldn't be too scared for the test. I think the material is pretty straightforward. And good luck. מה שכן הייתי רוצה לשאול אותך, אתם מעדיפים שיהיה חזרה למבחן קרוב יותר למבחן או יותר, כאילו, כמה שיותר מוקדם?
יהיה חזרה בכלל למבחן?
אני אעשה שיעור של 3-4 שעות.
שיהיה קרוב למבחן.
תראי כמה ימים כזה, שיהיה מצד אחד קרוב, מצד שלא יום לפני.
אני חופש, אני אנסה לעשות שבוע-שבועיים לפני.
אבל בהכנה למבחן יהיה לנו בעצם, יהיה לנו נקודות